welcome back to week 6 of the introduction. Week 6 of the thermodynamics course, and I'm sorry from my side as I have taken this class a bit late. It was supposed to be on Tuesday, but because of some circumstances, I had to shift the date of the class to today, Friday. So I hope it's this class will be helpful for the students who join, even though I guess more or less the solution of this week's the week 6 has been released, and moreover week 7's class will be on Sunday, this Sunday, same time 6 to 8. I hope this will be notified in the NPTEL portal as well. So apologies from my side for this confusion. There are some circumstances that was unavoidable from my side. That's why I had to do this skipping. So I hope that's understandable. So I'm really sorry for this entire confusion. Okay. So again, so for today's session, we will be again discussing with the two-phase system. Basically, we will dive deep into the concepts of pure substances, the properties of pure substances, and in this case, we will be primarily dealing with the steam or a liquid and vapor mixture of water. So we will be primarily discussing about that. So let's wait for 2 more minutes. Let's see if other students join. Otherwise, we will just continue with today's session. And as per our regular agenda, we will go through the concepts that were discussed in the class by Professor Anand, and briefly go through them because Professor Anand has extensively discussed this TV diagram, PV diagrams, and eventually we'll also discuss the TS diagrams. So, and we have discussed PT diagram as well in basically the phase diagram in the sessions. So Professor Anand has extensively discussed those diagrams, and I have those diagrams in today's session, but for the sake of saving time and focusing more upon solving questions, I guess I will not dive deep into the plots, but if there are any doubts, you can ask. I hope I will be able to clear them and discuss them properly. That's all. That's today's plan. So let's just wait for 1 more minute, 6:11, and then we can start. Okay, then I guess we can start. So let's begin with the TV diagram, basically the temperature versus specific volume diagram. So in today's session, we will be primarily discussing about the two-phase nature of the substances, specifically water in this case. So we will be discussing about steam and how to analyze such systems. So before this week's session, we were primarily dealing with single-phase systems, say gaseous or liquid systems. We were discussing about the application of the first law of thermodynamics to find out the net heat and work interactions. We also in the week 5 session, Professor Anand has also discussed about the concepts of moles, Avogadro's number, and a way of analyzing and understanding the perfect gases in a much more robust manner. But in this week's session, and consequently the week 7 part as well, we will be dealing with two-phase systems, so specifically steam in this case, and we'll try to understand how to analyze such kind of systems. And as Professor Anand has already mentioned, these kind of systems find the crucial role in the production of energy in our day-to-day life. For example, the nuclear power plants, the thermal power plants, all these power plants are based upon the application of these concepts, and are basically the generation of steam, and using that steam to rotate the turbines to produce electricity. And to understand those systems properly, we need to know the concepts of these two-phase systems. So that's why we are discussing about it in this week's session. So this diagram, TV diagram, this black line, this black uh, skewed dome, I would say skewed because it is skewed in the left side of the plot, so a bit skewed. So this skewed dome is known as the liquid vapor dome, primarily because it the liquid vapor region of the steam is encompassed within this dome. That's why it is termed as the liquid vapor dome. And the region in the left side of this liquid vapor dome, specifically this region, is known as the subcooled region. The region in the right side of this liquid vapor dome is known as the superheated vapor region, and the region above this critical temperature zone is known as supercritical region. Okay, so let me just try to go through it briefly by the example of heating water uh, at constant pressure. So this blue line, the sky blue line, sorry, is an isobar. This specifically means that we are heating a liquid at constant pressure and observing its different phases that occurs while it's heating. Okay, so point A denotes a state of liquid, state of water where it is in liquid state. So let us denote it as point A, where it is in the form of liquid or water, right? So let the temperature be Ta. Now if we heat the water to a set temperature B, where B denotes the boiling point of water, so it will be 100 degrees Celsius, right? So when the temperature of the water reaches to when the temperature of this water reaches 100 degrees Celsius because of the applied heat, uh, this point is known as the saturated liquid. This point is known as saturated liquid, right? We will see that what the saturation region means. Okay, now at this point the water is in equilibrium. The water is in, it has this liquid and vapor phases at equilibrium, right? So at this point, beyond this point, if we continue heating, so we will see no change in temperature. uh, can you say why? Like, you can comment in the comment box, like why there is no change in temperature. Like, we see that from point A to B there is a change in temperature, and we specifically call this as sensible heating. We see a observed change in temperature because the point has shifted from A to B, so there is a change in temperature. But why there is from, say, heating from temperature B to C, D to E, there is no change in temperature? What is this phenomenon known as, or why does it occur? Can anyone can you please tell? Yes, exactly. So as discussed by, thank you so much. As discussed by Professor Anand, this heat that is being applied to water is now being used to change the phase of water from liquid to vapor. Uh, Professor Anand, like, very beautifully explains by a very practical understanding. Like, here, since the pressure is constant, the heat applied is not used to increase the pressure, so there is no increase in pressure. Moreover, since the application of heat does not change temperature also, so temperature also not changing. So the only way where this energy will be used is to change the phase of the liquid, right? Change the phase of liquid to vapor to a higher energetic state. So vapor is in higher energetic state, so the energy from the heat applied is used to change the phase of the water from liquid to vapor, right? And this region or line denoted by B to E is specifically known as the phase change region, right? And the one important thing to note is that the pressure throughout this phase change process, at least in this given plot, remains constant. Okay, and this pressure is known as a saturation pressure for this particular temperature. Okay, say T, if T is the temperature at which the phase change is occurring, this constant pressure or the isobar is known as the saturation pressure corresponding to this temperature. Okay, similarly, if the liquid is being heated to, say, uh, at a different pressure, say P2, then the corresponding, it will have a different saturation temperature corresponding to that particular saturation pressure. Okay, we will see how this occurs when we discuss the next plot. Okay, so here
Now when the liquid is being heated from B to C, we'll see that the volume of the liquid has increased liquid or liquid vapor mixture has increased from B to C, so Vc is greater than Vb. Okay, but since the phase change is occurring in this during this point of time, the temperature at C is equal to temperature at B. Okay, so it is very crucial to know Tc will be equal to Tb, and we will now will have a liquid vapor mixture. Okay, I've just written water, but specifically it should be liquid. Okay, since we are discussing this dome for a generic substance, but right now I'm taking the generic substance to be water. That's why I have written water, but for a generic sense you can write it as liquid. Okay, there's no problem in that. So the temperature at C would be equal to temperature at B because of the phase change, right? Now when further heat is being applied, say the point has reached from point C to point D. Okay, given that pressure is constant, again the volume of the liquid vapor mixture is now far more greater than the volume of the liquid vapor mixture at point C, but the temperature remains constant still. Okay, so now you will see that since the volume of the liquid vapor mixture has increased, so what can you tell about the relative quantity of the vapor and the liquid phase? So in which case do you feel between C and D would have a higher vapor content? Okay, uh, yeah, like if we think in that way, you will eventually realize that at point D we will have a higher vapor content higher vapor content compared to the compared to point C. So point C will specifically have it's not necessary, but it will specifically have, it seems that it will specifically have a higher liquid content than the vapor content. And like after some point of time when the heat is being continuously applied, the liquid phase of water gets converted to the vapor state, so the amount of or the quantity of vapor in the liquid vapor mixture increases, basically the mass fraction increases. So the amount of vapor in the liquid vapor mixture is higher in the later stage of heating during the phase change, right? So the vapor content at point D would be higher than the vapor content at point C, which will eventually see that when the when we heat it further and it reaches point E, that point is known as a dry saturated vapor, right? So the liquid is still at saturation state, which basically means that the liquid vapor are still at equilibrium state, but it is being heated up to an extent that the net amount of uh, liquid in the liquid vapor mixture is equal to 0. So we have a dry steam, right? Basically we know there is a dry steam or dry saturated steam. So the at point T the liquid vapor mixture essentially has only vapor, right? So the entire liquid has been converted into vapor, so the entire mixture is only composed of vapor, right? So point E will again have a higher volume than point D, as you can realize from the location of the point E with respect to point D in the TV plot. But again the temperature at E would be equal to temperature at D, because still they are on the same temperature and the phase change is occurring because of the very fact that point E as well as point B are saturation points. Basically the liquid and vapor stage are equilibrium, so they are saturation points. So they are at the same temperature, right? But now if we heat this dry saturated vapor beyond point E or beyond the saturated state, now we will observe an increase in temperature, because beyond heating beyond point E will again incur a sensible heating from point E to F, which can be realized by the fact that the point has now shifted vertically from E to F. So there is a change in temperature, so we will observe a sensible heating. And now this point at this region at this substance at point F is known as a superheated vapor, right? So here also the volume of the mixture will increase, but not that rapidly as it increased in the case of phase change. So the volume of the vapor will increase, and the temperature of the vapor will also increase, because now it experiences sensible heating rather than latent heating. Okay, so I hope this and I will also discuss about critical point as well. So let us introduce it. Is it clear up to this point? I know the lecture was already done in the last week, but if any doubt, So any remaining doubt or question you can ask. Yeah, thank you so much. Thank you so much. Okay, so you will see that this this diagram is very peculiar, as I already mentioned in the initial state. It is a skewed dome rather than a uniform dome, or sorry for the drawing, rather than it being a simple uns uh, no, like normally distributed Gaussian curve, like that is the example I'm having right now, or bell-shaped curve or bell-shaped dome. It is being skewed in left-hand region, right? So there's a specific reason behind this structure. So let me just explain it for once. Then like I can ask you in the assignment, in the question solving part, like why, like, just to check your knowledge. But let me explain it for the first bit. So this shape is primarily because of the fact that we know that this region, or this line specifically, from this point to the critical point. So let me define critical point for this. Okay, then it will be much clearer. Okay, so now as I mentioned, this pressure P, say P1, let me just make it clearer, say P1, and this entire process that I mentioned here is done at constant pressure P1, which is known as saturation pressure, right? And this pressure will have a corresponding saturation temperature at which the boiling, at which the phase change starts to occur, right? So temperature at say TB or T1 say is the corresponding saturation temperature for this particular saturation pressure. Okay, now if we increase this saturation pressure, say if we increase the pressure to P2, you'll observe that it will again have a different corresponding saturation temperature, right? Or basically it will mean that if we increase the pressure at which we are boiling the liquid will the liquid will start to boil at a higher temperature. That's the very concept of pressure cooker, right? We pressurize the air above the substance that we are cooking and increase the temperature at which the water boils, right? So that's the very concept of pressure cooker. So if we increase the pressure, the corresponding saturation temperature, the temperature at which the boiling starts to occur, or phase change starts to occur, also increases, right? So we'll see that the the corresponding isobar will take this form. Right, it will take this form, and it will have a different higher pressure, so higher temperature. Yeah, of course, yeah. So it will correspond to a higher saturation temperature, right? T2, a higher saturation temperature now. So, and this trend continues to occur. You will see that now if again we increase the pressure, the saturation, corresponding saturation temperature will increase, and you will see that we will reach a point, say P equal to Pc, at which and one more thing we'll also observe that as we increase the pressure, this required heat for phase change, or the region of phase change, also decreases. So you'll see that the extent of the region at higher pressure is comparatively lesser than the extent of the phase change region at lower pressure, and this trend continues to increase because of the very nature of the curve. So now if we reach, say, at this point, you will clearly see that the phase change region at this point is much lesser than the phase change region at this point, which was at lower pressure, right? So now if we increase the pressure up to an extent that this phase change region basically becomes a singular point, so that will, this point would correspond to the critical point of this particular substance, or water vapor, water in this case, right? So the critical point would be the region at which no phase change occurs. So the liquid directly changes to vapor rather than having a phase change. Okay, rather than requiring a phase change region, the liquid directly changes to vapor. There is no discernible discernible region or period of phase change, so liquid rapidly changes to vapor, right? So that point is known as a critical point. So at that the pressure at that point will be known as the critical pressure, and the corresponding temperature will be known as the critical temperature. And this critical pressure and temperature are distinctly denoted in the steam table that will eventually use to solve problems related to this two-phase systems. Okay. hope the concept of critical point is also clear. Okay. So now regarding the shape of this curve. Okay. So we know that if we apply heat, right? If we apply heat, the substances tend to expand, right? Given the fact that even if you are dealing with water, given the fact that the temperature of water is higher than the 4 degrees Celsius, the anomalous region where the water tends to expand when being the water tends to contract when being cooled down, the anomalous region up to 4 degrees Celsius. Considering that we are having water at room temperature, say, so the water, so I'm considering water as an example in this case. So if you are heating water, it is bound to increase the specific volume of its specific volume, right? So as we increase the temperature, the volume of water increases, right? So specific volume of water increases. So there is a slight curvature in this. There is a the curve tends to have a positive slope, right? Now we also know a fact that as we go upwards in this curve, the pressure is also increasing. Uh, yeah, exactly. Yeah, that is what I was going to say. Like, this is a function of both pressure and temperature, and they interplay in a way that they try to cancel out each other. Like, they play a role opposite to each other. Right? The increase in temperature will expand the substance, and increase in pressure would contract the substance. So in the case of liquid, the increase in temperature increases the volume of the liquid, but the increase in pressure that is also experienced as we go up the curve, the increase in pressure would result in the contraction of the contraction of the liquid. But this change in the pressure in the volume of the liquid because of an increase in pressure is much more less or comparatively lesser than the expansion of the liquid experienced because of the applied heating or increase in temperature. And that's why this slope tends to have a positive slope, right? Now you in the case of a vapor, you'll see that this, as the temperature is increased, you will have a negative slope, primarily because of the fact that the effect of pressure now trumps the effect of temperature. Like, increase in the contraction in the vapor because of an increase in pressure has far more greater effect than the expansion of the vapor because of increase in temperature, and that's why we are having a negative slope. Okay. And regarding the slope of this curve, or the steepness or the shallowness of this curve, is primarily because of the fact that this change in the volume because of the change in pressure or temperature is much more discernible in the vapor state compared to the liquid state. That's why we are having a very steep slope, a very slight change in the specific volume because of even in the change in temperature or pressure in the case of liquid, right, or the saturation liquid line. And but we are having a very discernible or clearly observable change in the volume of the liquid, the volume of the vapor, because of the interplay between the change in pressure and temperature, and thus we have a very shallow curve beyond the critical point in the left hand side, or in the saturated vapor region, right, or saturated vapor line. So I hope it was clear. I know that this is already discussed in the lectures, and the other TA might have discussed clearly, but just for revision I am discussing it. Okay, I hope that's fine. I hope it is clear. Okay, yeah, thank you. Like, this is something like, it's a very conceptual question. Like, uh, it's usually asked in many interviews, so I thought that it would be good to discuss about it. Right. So again, there is a, as I mentioned, there are two types of heating that's observed in this diagram. There is the sensible heating from point A to B and E to F, which is denoted by MC delta T. So for sensible heating, we'll observe a change in temperature. That's why a change in we have a delta T term in the heat addition term. Okay, in the heat addition expression. Okay. Similarly, in the case of we also have a latent heat region or phase change region where we experience heating without a change in temperature, and that's why, and that kind of heat is known as a latent heat or a hidden heat, because we do not see any change in temperature, right? And in this kind, an expression for this, the expression for this kind, the expression for this kind of heating will observe uh, no 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 would observe no temperature term, right? There is no temperature term in this expression, and thus this QLH, or the latent heat per unit mass, is usually mentioned, and this is actually you can find it in the steam table. I will eventually show you how. I guess this was also discussed by Professor Anand in the lectures, but you will eventually see that this is already given in the steam tables. So you just need to apply it to the mass of the liquid that is being heated to obtain the latent heat. Okay. So, and most of the questions uh, regarding boiling of water or phase change will usually exclusively mention the latent heat of vaporization or latent heat of fusion in the question. You just need to apply it accordingly to find the net heat applied during the phase change. Okay. So so these are the key points that was obtained from this diagram. That is water the okay, I'll just go through it once. Water contained in the constant pressure device heated slowly. So that is the physics that we are discussing. The volume changes continuously because of the applied heating. T increases only when the temperature increases only when the water exists in a single phase. Basically, we are having sensible heating, right? And during phase change, the temperature and pressure remain constant because they are fixed by the saturation state, right? The saturation pressure fixes the saturation temperature, okay? And heat transfer without temperature, and during phase change, there is heat transfer without any temperature increase, okay? So these are the key points about this discussion that we have right now here. So this is something again that I already discussed, the concept of critical point, right? As you can see, at 100 degrees Celsius, or say at P is 0.1 megapascal or 1 bar, it is basically around, it's not exactly that 1 atmospheric pressure, but around 1 atmospheric pressure. You will see that the corresponding saturation temperature is almost equal to 100 degrees Celsius. In reality, it will be 99.6 degrees Celsius for 1 bar and 100 degrees Celsius for 101.325 kilopascal. It is atmospheric pressure, right? So the saturation temperature corresponding to the pressure of 0.1 megapascal, 0.1 megapascal is 100 degrees Celsius. Sorry for this mix up. Now, if we increase this pressure, or the pressure at which we are heating the liquid, say pressure, if we increase the pressure to 1 megapascal or 10 bar, you see that the corresponding saturation temperature now also increases to 185 degrees Celsius, right? And similar trend will be observed if we increase the pressure further. So if we increase the pressure up to a point, say P equal to PC, which is a critical point, pressure which is equal to a critical point, you will see that at the critical point, the temperature is 647.1 Kelvin, and the corresponding critical pressure for water in this case is 22.064 megapascal. Okay. So these are values that are standard values for water. So it is good to know, but no need to memorize, because this will already be given in the steam table. Okay. Okay, so this is something that I already discussed. I will not go through it. Yeah, so these are the key points to obtain from the plot that I right now discussed. At low pressures, the latent heat of evaporation is high. At high pressures, the latent heat of evaporation is lower. At PC, the latent heat is zero. The critical and the corresponding temperature is the critical temperature, and the corresponding volume is known as the critical volume. And at critical pressure, both volume and temperature, above the critical pressure, both the volume and temperature increases with heating. Okay. So I hope these 4 key points are clear, because I discussed it right now. I'm just discussing the key points that we obtained from the plot. I hope it is clear. Any doubt in these 4 points? Professor Anand devised the discussion in very simple points. I hope it is clear. Okay. Yes, thank you. Yeah. Similarly, if you are discussing about the constant pressure lines in the case of ideal gases, so you from the ideal gas law we get that T equal to P by R equal to V, right? or basically is obtained from PV is equal to MRT, or P into specific volume is equal to RT. So from that you will get that T is equal to PR by V, where V is the specific volume. Okay. So in the case of ideal gases, these constant pressure lines are straight lines on a TV diagram. Okay, it's understandable because this is basically an equation of straight lines having a slope of P by R. Okay, so the equation in the TV plot, this temperature, if you represent temperature as a function of specific volume, so the slope, the uh, curve for the temperature will be defined as a straight line having a slope of P by R, and the slope of this curve will be determined by the pressure, because R is a universal is a constant for a specific gas. So P would determine the slope of this curve, and thus you will obtain a straight line in the case of ideal gases in a TV diagram. Okay. Similarly, to analyze the systems, you can also discuss the similar analogy in the PV diagram as well. So now in this case, we'll have a pressure versus specific volume plot, and these blue lines, these constant regions or constant pressure lines, are actually the regions that indicates constant pressure are actually now isotherms. Okay, so this corresponding temperature, say T1, T2 or T3, would fix the saturation pressure. See, this is very crucial. Okay, I discussed about it in the previous classes. There is F plus C is equal to C plus 2. This is the Gibbs phase rule. So F is the degree of freedom of the system, P is the number of phases, C is the number of components, and 2 is just a constant, right? So now if I consider a single component system, so C will be 1, so F is unknown, and P, if we consider 2 phase now, if it becomes 2, then we will have F equal to 1, right? So F is the degree of freedom, that is, or the number of variables or free variables that we require to fix the state of the system, right? So in this case, you will see that in the case of phase change, because number of phase will be 2 only within this vapor dome, right? Liquid vapor dome, right? So the number of phase is 2 in this vapor dome, liquid vapor dome. So if we fix that, say it is a pressure versus volume plot. So if we fix the pressure, it will automatically fix the temperature of the system, and we can get the state of the system, right? So just by knowing the pressure or temperature, at least in the case of these two-phase systems, in the liquid vapor dome, we can easily find the state of the system. Okay, so just knowing the saturation pressure or the saturation temperature, you can easily find out the corresponding saturation temperature or saturation pressure. Okay, so they fix each other. So similarly, in the PV plot, if we know the temperature or the saturation temperature, it will correspondingly fix the saturation pressure at which the phase change occurs. Okay, is it two property rule? No. This Gibbs phase rule can be applied for any component or any phase systems. Okay, system any phases. Okay, we will eventually see that. I will apply this to the triple point as well. So in the case of triple point, we will have P equal to 3, right? So now if P becomes 3, then F becomes 0, right? So there is no variable that we need to define because triple point is fixed, right? Similarly, outside the vapor dome region, P becomes 1, right? P becomes 1, then F becomes 2. So outside the vapor dome, liquid vapor dome, we require two independent states of the system, two independent variables to define the state of the system. Because outside the liquid vapor dome, say at this region, if you define the temperature, you won't know what's the state of the system. You need to know, say, not at this isotherm, say at this temperature, say if you are, say at this, even at this point, even at this temperature, if you want to define the state of the system, you need to find the corresponding temperature, because at this point the pressure is not fixed, right? You need to find the pressure to define the state of the system here, because the saturation pressure is not fixed. You cannot find the saturation pressure at this point. So that's the beauty of Gibbs phase rule. So it gives a very nice idea about how to define a state of system, what are degree of freedom required to define the state of system. So that's why the Gibbs phrase rule becomes handy. Okay. So an important conclusion from this plot was again that the critical isobar is a horizontal line on a PV diagram. Okay. So critical isobar, the pressure corresponding to the critical temperature is not a critical pressure or a critical isobar. Okay. And one more important conclusion that Professor Anand deduced from these diagrams is that the isotherms in the superheated region, uh, for water at least, tends to be hyperbolic. Okay, so nearer nearer to the in the we previously discussed in the where we discussing the first law of thermodynamics and the different PV PDV works. So we discussed that uh, for the isothermal processes, the uh, PV plot would be an rectangular hyperbola, right? So in this case also, that was for an ideal gas, right? That was for ideal gas. But in the case of water also, as water as well, it is for water vapor, very far away from the liquid vapor dome, it is at the very highly superheated regions. These isotherms also tend to behave as rectangular hyperbolic. Okay, so that's a very important conclusion deduced from these plots, that at very high temperature and obviously at high pressures, the sorry at very high temperatures, not at high pressure, at very high temperatures, this water vapor can actually behave as ideal gases. Okay, but not nearer to the liquid vapor dome, not at those phase change regions, but at very high temperatures, it is far beyond the boiling point of water, these isotherms will behave as rectangular hyperbolic. Okay, and basically it will conclude that the water vapor can be treated as ideal gases. Okay. So again, saturation state. So Professor Anand defines saturation state at this point specifically, the state at which the change of phase may occur without a change in pressure or temperature. Basically, the liquid vapor and the liquid and vapor are in equilibrium. Okay, and at that particular state. Okay. So these are the various lines. I already discussed it, so I won't go further. So if you have any doubt, you can ask. Okay. So yes. So now the phase diagram. Okay. So if you have any doubt on the phase diagram, you can ask me here. But I feel that uh, Professor Anand, I guess, took one entire lecture to explain this very properly. So I will just go on and discuss the key points in this plot. Okay. So the one or a very important conclusion is that, and this diagram is not for water. Okay, it's for substance that contracts. Sorry, it is for substance that contracts monotonically during freezing. Okay, monotonically means it will continue to decrease the it will continue to contract as we freeze it. Okay, or the density of the substance will continuously increase when you freeze it. Okay, so it's for that substance, this particular PT diagram or the phase diagram. Okay, so phase diagram, as the name sounds, is used to distinguish the different phases used to distinguish the different phases, and that for that purpose only this diagram was devised. So the in this diagram, the phase change is represented by a single point. Okay, why? Because you can see that uh, the liquid vapor region is separated by a single line. So of course there is a, since they are below the critical point, there is a phase change occurring, but that phase change region is not temperature constant. Okay, so single point. Yeah, of course. So they are not the phase change region is not distinctly uh, determined, so distinctly shown. So the phase change region is only determined by single point here, as already mentioned. So at a particular temperature, of course, it will fix the corresponding pressure. Say saturation pressure, the phase change region would be determined by single point in this region, okay, in this plot, okay. And now comes the concept of triple point. So triple point is basically the region where the three phases of the substance, the solid, liquid and vapor state are in equilibrium, okay. So as I mentioned in the Gibbs phase rule, so F plus P, sorry, let me just write it again. F plus P is equal to C plus 2. So considering it as a single component system, so C will be 1, it is 2 again, and phases are 3 at the triple point, right? So F should ideally be 0, right? So degree of freedom is 0, so triple point for any substance is actually fixed, okay. So one more conclusion was that the triple point exists for all kinds of substances, okay. That was again very important conclusion. And this plot, I'm not going to go through it very extensively, but this plot is now for the this is the phase diagram for water, and you can see that there is an anomalous behavior that where the increase in pressure results in a decrease in the specific volume. So increase in the pressure results in a decrease in the specific volume, or increase in the pressure results in a decrease in a specific volume, and this is shown in this region, okay. So this region is specifically occurs, this anomalous behavior is usually occurring within a temperature zone of 0 to 4 degrees Celsius, where you will observe that when we heat the water, or if we increase the temperature of water from 0 to 4 degrees Celsius, the density of water, rather than increasing, it decreases, and the water is has the highest density at 4 degrees Celsius. So there is an anomalous behavior of water, and if we freeze the water from that point, you will see that there is an expansion in the water, or basically density of water decreases, right? That's specifically because of, like, I'm also not quite sure, like maybe because of hydrogen bonds in the water, how their behavior. So that was not discussed in that lectures, but it may be primarily because of that, okay. So if any one of you know, you can please tell, like, who are good at chemistry, you can discuss it here, but that's what specifically the reason behind this anomalous behavior of water. And we were discussing it here because we need to take, when we are dealing with water at that temperatures, usually we handle water, or in the, say, in the thermal power plant or in the nuclear power plant, the temperature of water is usually way beyond the triple point, or way beyond this anomalous region, right? So we are not usually encountering it. But if we are at all going to understand the behavior of water at these temperature regions, we need to take into account this anomalous behavior, and that's why this diagram was discussed. So I will suggest that, sorry from my side that if I'm not able to make it much clearer, but I will suggest that if you have any doubt, or if you want to know more, you can go and revisit this lecture, because Professor Anand extensively discussed this plot. I'm not going to do it for the sake of saving time and discussing problems related to it, but if you have any doubt, you can go back to the lecture and just clear your doubts, okay. Or if you have any doubt, you can just ask in the discussion forum as well. So I hope it was clear. Yes, no would be fine. Yes. See, what I'm trying to say is that most of the problems or questions that we are going to encounter would be from the thermodynamic point of view, right? And sorry for the abrupt noise. Okay. So from the thermodynamic point of view, I'm extremely sorry. I'll just try to close the window so that this noise is not there. Just give me 1 minute, okay? I'm sorry for this disturbance. Sorry for the noise. Okay, so what I'm trying to say is that from the perspective of thermodynamics, dealing with two-phase systems is primarily because of understanding the functioning or the working principles of thermal power plants or nuclear power plants, right? And in those power plants, the temperature scale that we are dealing with or the pressure scales we are dealing with are usually at megapascals and beyond the boiling point of water or near those regions, right? So we'll never come at a point where we will be dealing with this anomalous behavior of water. So from that perspective, it's not necessary to know this behavior, but just as a added knowledge or added understanding to the behavior of water, Professor Anand extensively discussed about this in the phase diagram. Okay, so I request that you go to the diagram if you need any clarification. But from my perspective, I am saying that you don't need to actually deal with this behavior while we are solving the problems. Okay. So now comes the concept of the dynamics fraction. Okay, so to make it interesting, no, I guess we can just go through the expressions and we'll find it more interesting while we solve the problems. Okay. Okay. So the dynamics fraction or the quality of the steam, these are two terms that can be used interchangeably in the questions or in any thermodynamics book. So it's good to know that both are the same thing. Okay. So it's basically the fraction of the mixture that is in vapor phase, or the amount of vapor in the liquid vapor mixture. Okay, that will be given by the mass of vapor in the liquid vapor mixture over the total mass of the mixture. It is mass of the vapor plus mass of liquid. Okay, so there's a very simple derivation to find the use of the dynamics fraction to determine the volume of the liquid vapor mixture within the liquid vapor dome. Okay, so if m equal to mf plus mg, for here the mf denotes the mass of the fluid and g denotes the mass of the gas, because we will be dealing with different kind of substances, so we are using a generic form. Okay, so again v here is the total volume. Okay, not the specific volume but the total volume. Okay, it's capital V. So v is again the volume of the fluid plus the volume of the gas. Okay, so now if we dissociate it into the specific volume and as a product of the specific volume and the mass of the corresponding mass of the vapor or the gas, so vapor or the liquid, we will get that mv is equal to mf vf plus mg vg, or we can substitute mf as m minus mg, so m minus mg into vf plus mg into vg. So if we take mass in the denominator, m as in the denominator, we will get that v is equal to 1 minus mg by m into vf plus mg vg by m. Okay, and we know that mg by m is the dynamics fraction x. Mg by m is the dynamics fraction x, so we will get v or the specific volume equal to 1 minus x vf plus x vg. Okay, or we can play with this expression further to get that the specific volume v is equal to vf plus x vfg, where vfg is Vg minus Vf. Okay, or basically the difference in the volume of the gas and the fluid. And always remember that, I know it's very basic, that Vg will always be greater than Vf, and they are only equal at what point? At what point do you expect the volume of the gas and the volume of the fluid to be equal? So this is the liquid vapor dome. So volume of fluid would be here, volume of the gas would be here. So at what point do you feel that the volume of the fluid and the volume of the gas would be equal? A conceptual question. You can try it out. In dry saturation steam. No. Let me just make the question a bit more clearer. Okay, so if this is a TV plot, so this point would correspond to Vf, right? The volume of the fluid, specific volume of the fluid. This point will correspond to the volume of the gas, right? Vg. So you can clearly see that the volume of the gas for a particular temperature and pressure or a particular saturation state is always greater than the volume of the fluid, right? It's understandable, right? But there is a region or there is a point where you find that the volume of fluid is actually equal to the volume of gas. So what is that point known as? Just try to go upwards in the diagram, then you'll get a hint. CP, yeah, critical point, yeah, exactly. So if we go up to the diagram, then again say if you are dealing with a fluid at this steam at this particular saturation temperature or pressure, you can see then the difference between the specific volume of the gas and the fluid has reduced, and you'll see that this trend continues up to the critical point. Uh, say C, I don't know what how to denote it. I just write it critical point. I'm not writing CP. Thank you. I'm not writing CP because it may be confusing with the specific heat at constant pressure. Right? Sorry for that. So at this point, you will see that Vg would be equal to Vf would be equal to Vg, and this thing you will observe when we are discussing steam tables. Of course, I'm not going to entirely go through the steam tables one by one, but you will be going through it, and you will see that at the critical point the volume of the fluid and the volume of the gas are identical. Okay, and this is a very important expression. Let me just put it in the rectangular box, red box means it's very important. Okay, so and this expression can be used to determine any other thermodynamic property. Okay, so in the steam table we will primarily dealing with let me use different colors, say green. So we will be dealing with the internal energy. So U would be again by determined by UF plus X VFG, sorry, UFG. The enthalpy HF plus X HFG, and entropy SF plus X SFG. Okay, so Professor Anand mentions that he will not be discussing about entropy right now because we have not right now discussed the second law of thermodynamics and correspondingly not understood what really entropy is. But for just for the sake of introduction, a brief introduction, or a sake of understanding, let me keep it as such in the questions that we are having. So right now just take entropy as another thermodynamic property. Okay, just a generic take it as a generic thermodynamic property for now, because we have not defined it and we do not know what entropy actually is, and that's why Professor Anand didn't discuss about TS diagrams of this liquid vapor mixtures. Okay, so right now just take it as another thermodynamic property. Okay, so let us now, I guess that's all for the discussion, but let us now discuss some questions. Okay, I guess all of you have already done the assignment, so it will be quite easy for you. Then you can help me out to solve them as fast as possible. Okay, so let us go to question number 1. Yeah, I hope both of you have steam tables in your hand, like hard copy of steam table or digital copy, doesn't matter, but you will have to use it. Okay, so let's go to question number 1. With reference to the steam table provided, I hope you have it. The specific volume of the saturated water vapor in at 4.8 degrees Celsius is. So let me just see here. Okay, so this is steam table. Oh no, I don't know how to rotate it, but bear with me, forgive me for this inconvenience. So from a steam table, I hope both of you know how to use the steam table, right? Or should I take one example? Take this example. Should I take this example? Okay, thank you. So, and I hope you're okay with this setup. That this still, I don't know how to rotate it because it's PDF form, and oh, we know, right? Okay. Okay then, let me just take this example. So you can see from the I hope, yeah, yeah, it's great now, yeah. Great, it works. Okay, so from the question, oh, has anybody answered it already? Okay, no, fine, fine, no need to answer. Let us just try to solve this question. So from the steam table, let me go back to the question. We need to find the specific volume at the of the uh, saturated water vapor at 4.8 degrees Celsius. Okay, so you will see that saturated steam. Okay, now we are discussing the saturated steam, basically the region within the liquid vapor dome. Okay, so our required temperature is not in the steam table. It's not distinctly given. Higher, better steam tables, or like what to say, thicker steam tables having more number of pages in the book will have more temperatures, but this is some from the appendix of a book of Pikenak. So uh, here we have 0.01 degrees Celsius and 5 degrees Celsius. So our required temperature is 4.8 degrees Celsius, right? So we need to apply a concept of linear interpolation. Okay, so I will show you what it basically means. So we'll just uh, assume that the variation of the all thermodynamic properties with temperature is linear, mainly because of the fact that the temperature difference between the readings is very less. So we'll assume that within these small differences the properties vary linearly. Okay, so we need to play with uh, the value of this specific value of the saturated vapor, right? This one. So let us go. So you can note it down. At T equal to 0.01 degrees Celsius, the volume of the gas, the saturated vapor, is 206.132. Okay. Similarly, the at temperature equal to 5 degrees Celsius, the volume of the saturated vapor is 147.118. So we are observing that the volume of the vapor decreases with the increase in the saturation temperature. Of course, we saw from the diagram that as temperature increases, the volume of the saturated vapor will go on decreasing. Okay. Oh yeah, yeah. It's completely fine. No problem. No problem. You need to know the concept. Okay. And I hope the solutions would be agreeable to certain decimal points. So I hope that's fine. Okay. Just need to, yeah, just need to know the concept. Okay. Let us see if it is agreeable with the solution of the, but not in the range. Okay. Okay, that's fine. There's nothing that we can do about it. So because of the limitation of the steam table that we have in our hand. I'm sorry. Okay, so let us go back to the problem. So we have that at 0.01 degrees Celsius. Yes, yes, you have to do that. You have to do interpolation. And that is what I'm exactly saying, that if the interpolation answer, well, you can write the answer on the screen. Let us just check whether it matches with ours. Right. Okay. So at T equals 0.01 degrees Celsius, Vg is 206.132, and at 5 degrees Celsius it is 147.118. Okay, so we need to find the corresponding Vg at T equal to 4.8 degrees Celsius. So we do linear interpolation, as you already, as you both of you agree that you already know. So just for the sake of other viewers as well who will watch the video, let me do this one. So at T equal to, let me take T as our variable because we know the value of T in hand. Okay, so at T equal to 0.01 degrees Celsius, the corresponding specific volume is 206.132. Okay, similarly at 5 degrees Celsius we have specific volume as 147.118. Okay, we do it right here, and we know that the temperature given is 4.8 degrees Celsius, which is between 0.01 to 5. And Similarly, this specific volume will also be in between 147.118 to 26.132. Okay, so the very concept of linear interpolation is that the slope of both these lines, say this entire line, or whichever we want to, however the way you want to interpolate, say these two values or these two values, is completely your choice, would be the same. Okay, so the slope of the line will be determined by using the y value, the difference in the y values over difference in the x values, right? Or in this case, the value difference in the specific volume over the difference in the temperature. So we'll have 147.118 minus 206.132 divided by 5 minus 0.01. Okay, always take the corresponding values, don't get confused with the diagram. The corresponding specific volume of for 5 degrees Celsius is this, so take this, and specific corresponding specific volume for 0.01 is 206.132, take that. Okay, so these are known values, so you write it here. So similarly now for my choice, I have taken this region, I have taken this line, so you can take this line as well, there is no issue with that. Okay, so we'll have 147.118 minus V will be equal to 5 minus 4.8. Okay, so once you do that and do the calculations, you will find that specific volume V is equal to 149.4832 in my case. And of course there will be slight change in decimal values, but I hope that is agreeable. Let's see what solution that you give. Okay, so this is the way we do the linear interpolation. I hope this is clear. Even if you know, like if you have any doubt or any confusion from my approach, you can just ask. Okay, is it clear? Let me go to the next question. Okay, so let me take this question as well. Okay, let me discuss with both of you, and let us try to understand like whether the concept is clear in this case, because if this question is clear, then I can leave the rest of the questions to you to solve. Okay, for this today's session, this is one of the problems taken by Professor Anand in the lectures. So we have that 4 kg of saturated water steam mixture in an enclosed rigid container is enclosed in a rigid container at an initial pressure of 2 bar. Okay, pressure and rigid container, keywords. Okay, and 4 kg mass of the liquid vapor mixture. When the mixture is heated, it finally attains a critical state. Again important. So final state is a critical state now. Okay, that's very crucial to know. Find the initial quality of the mixture and the heat transferred to the system during the process. Okay, it is discussed by Professor Anand, but I'm just revising it so that we can understand the concept once properly and then solve the problems again, because this, I guess this problem more or less takes into account all the concepts all together. Okay, so we have mass as 4 kg, the mass of the mixture as 4 kg, then initial pressure is 2 bar, and final pressure is the critical pressure PC. Okay, because the final state is at the critical state. We need to find the initial quality of the steam, right, and the net heat transferred during the process to heat the steam to the critical state. So from the first law of thermodynamics, we have dq is equal to du plus dw. Okay, considering the fact that there's only PD work involved, the net work done would be 0, primarily because of the fact that the container is rigid. Okay, so there is no change in the specific volume of the liquid vapor mixture, so dV is 0. Yeah, of course. Now let us just draw the diagram. Let's try to draw the diagram for the process. So the liquid is, the state of liquid is within the liquid vapor dome. So the initial state is at, say, at 0.1. Okay, so we heat it by the addition of energy and take it to state 2, to which is the critical state. Okay, so one thing to know is that the process of heating is isochoric. Why? Because the this container is rigid, so the entire heating process is done at a constant volume process. So that is a very crucial point to have in our hand. Okay, so the heating process would look like a vertical line in the TV diagram. Okay, so we'll have V1, capital V1 equal to capital V2, or consequently we will have small V1, which is a specific volume at 1 equal to specific volume at 2. Is this point clear? Because V is specific volume is equal to volume per unit mass, and mass is constant and the volume is also constant, so the specific volumes are also constant at the final and the initial point. Okay, then we can write this, the initial volume, as Vf plus x Vg minus Vf, right? I guess this expression is also clear. We just derived it some a few minutes before. So from here we can determine x as V1 minus Vf divided by Vg minus Vf. Okay, so the unknowns in our hand are Vf and Vg. Okay, V1 we already know. So now let us go to the steam table to and V1 we will know because we know the volume of the mixture at a critical state. Okay, so let us go to the steam diagram to verify this. So at a critical state, I hope it is given here. Let me just check whether it is given in this diagram or not. So highest temperature should be critical state. So meanwhile, both of you can check in your steam tables as well. Okay, let me just verify it here in my table whether it is mentioned here or not. Okay, so it seems that my table does not include the critical state in the table. So is it given in your tables? You can just verify me. Let me just check in the book once again. Can you just look at the steam tables and let me know whether the critical state is defined in your tables as well? Okay, so it's not given here, so unfortunately. So let us just go to the values that we have in our hand. Okay, so at the critical state from the steam table that was used by Professor Anand, we get that the specific volume of the fluid at a critical point is 0.03106 meter cube per kg. That is equal to V2, and the internal specific internal energy at the critical point is 2015.7 kilojoule per kg. This is equal to U2. Why we are finding critical energy? Because we already got that the net heat applied to the system would be equal to the net change in internal energy. Okay, so we need to know the change in internal energy of the system. Okay, so now at 2 bar we find, because we already know now V, so we need to know the value of Vf and Vg at 2 bar, right? So at 2 bar we have Vf is equal to, now we can now I guess check the values of the uh, fluid at 2 bar. I guess that is available in the steam table that we have in our hand. Okay, so at 2 bar that would be basically be 200 kilopascal. So we have to, yeah, 0.2 megapascal, right? So let us just rotate this page. Yes, so now we have 2 bar in our hand, so it is basically 0.2 megapascal. Okay, so at 0.2 megapascal we have Vf as 0.001061 meter cube per kg and Vg as 0.8857. Okay, we can also take the value of Uf, Ufg and Ug as well. So basically we need Ufg, so you can take this directly. Okay, so value of Uf at 2 bar is 504.47 and Ug is 2529.5 kilojoule per kg. Okay, all units are in kilojoule per kg for the internal energy and the enthalpy. Okay, specific enthalpy and specific internal energy. So if we take those values, okay, so if you take those values now, then just substitute it in this expression. So we will get that x is or x1 is equal to 0.003106 minus Vf is 0.01061 divided by 0.8857 minus 0.001061. So once you calculate it, you will get that x1 is equal to 2.3 into 10 to the minus 3, right? And now you can use this value of x to find the value of the internal energy at the initial condition, at the initial state, right? Because you already know the value of Uf and Ufg, you will get that U1 is equal to 504.5 plus 2.3 into 10 to minus 3 into 2201.5 to get that U1 is equal to 509.56 kilojoule per kg. Okay. Is that clear? Okay. So now since you know the value of the internal energy at the initial state and the final state, then you can easily apply it to find the net heat transfer. Okay, so Q1 to 2 would be change in the internal energy, or M into delta small u, where small u denotes the change in the specific internal energy. So M is 4 kg. So just subtract this this from this and multiply by 4 to get that Q1 to 2 is 6024.56 kilojoules. Okay, check the units. It will not be by per kg because it is multiplied by the mass, so we will get the net heat supplied to the system. Okay, so I hope this was clear. Let us now go to the questions that we have in our hand for today. Okay, so let us go to question number 2. One is already done, so let us go to question number 2. Pure water at atmospheric pressure is at 0 degrees Celsius. When it is heated, its specific volume, what happens? So decreases steadily, increases steadily, first decreases and then increases, first increases and then decreases. So you can let me know what's the option number C. First decreases and then increases. Okay, so I have both of you answered the same. Okay, yeah, that's correct, because it's water and it is at 0 degrees Celsius, right? So now it is the point of the region of the anomalous behavior of water, and that's why Professor Anand was discussing about this in the lectures, right? So since we know that the density of the water initially, yeah, and initially increases up to 4 degrees Celsius. So increase in density will correspond to a decrease in the specific volume, right? So the specific volume decreases up to 4 degrees Celsius and then increases. Okay, so let us go to question number 3. Find the saturation temperature, the changes in specific volume and the entropy. So entropy you can leave, okay, I'm not forcing you to find it, but for your case, just let us find out the saturation temperature and the changes in the specific volume and the latent and the latent heat of vaporization for a steam at 1 megapascal. Okay, so you need to go to the steam table and find these corresponding values and let me know the solution. Okay, I'll give you say 5 minutes. You can write your answers in the, okay, let me just give the keywords. So changes in a specific volume, so I need to find VFG. You can leave the entropy for now, and HFG. I will wait till 7:28. You can write your answers on the screen. Okay, use the steam table and then let me know. Okay, let me just check. 179.8, 179.8, 179.9 from steam table. Okay, so yes, thank you. Now tell me the latent heat of vaporization, HFG, specific volume. Yeah, okay, is it? Let me just check the answers. Oh. Is it the change in the volume or you're just mentioning a specific volume? I want VFG, not VF or VG. Let me just check. Okay, yeah, it's in the right range. Okay, it's correct. Now tell me the change in the enthalpy, HFG. Yeah, it's correct. Can you tell me the change in the enthalpy as well, HFG? This, yeah, you can find it. Take your time. Find HFG as well. 2014.6. Yes, it's correct. Yeah, yeah. Thank you so much. So let me just go back to my answers and rectify it. Uh, yes. So at 1 megapascal from the steam table, we had the saturation temperature as 179.91 degrees Celsius. It varies from table to table, so just for forgive me for the variation in the decimal points mostly. So yes, then Vf is corresponding Vf at the saturation temperature is 0.001127 meter cube per kg, and Vg is equal to 0.19444 meter cube per kg. Then change in the specific volume is Vg minus Vf, so it turns out to be 0.1933 meter cube per kg. Yes, and the change in the latent heat of evaporation or the change in enthalpy is 2015.3 kilojoule per kg. Okay, so and for just as a general suggestion to other viewers who will watch the video is that for this session I will suggest that please have a hard copy or a soft copy of the steam table in your hand so that you can verify these values. Pause the video and then verify the values of the Vg and Vf, all the other thermodynamic properties, and then see how it works on, because it's very difficult for me to cross check all the values in the steam table and put in the recording. So just for the sake of saving time and other students in the lecture video at this point of time, I am not going to do this entire process, but for you I'll suggest it's a good practice to verify the values. Okay, thank you. And it's just a suggestion for all the other viewers who will watch the video. Okay, thank you. Let us go to the next question. Okay, so the next question is uh, find the enthalpy, and again if you want you can find entropy, but it's not necessary. Let's just deal with enthalpy now. Find the enthalpy of the steam when that pressure is 2 megapascal and the specific volume is 0.09 meter cube per kg. It's a bit more tricky than the previous question. So specific volume is given and pressure is given. Okay, so I will suggest you two, three steps. So first, for the since you're it's told that if it's not mentioned that it is in the okay, the thing is, so first check the value of the specific volumes for 2 megapascal and check whether the value of the specific volume is within the value of Vf and Vg. Can you please check in the steam table and let me know? The value of Vf and Vg for 2 megapascal. Let me just also try to look into it. 2 megapascal, right? So okay, it seems some pages are missing from my steam table. It's very unfortunate. Oh, I'm truly handicapped in this session. Extremely sorry for all the viewers and both of the students in the session as well. Like, my steam table is not good. Okay, and what's the Vg? Can you tell the Vg as well? You can just check whether 0.09 lies within this region. So of course it's greater than Vf. So is it lesser than Vg? And that's why I feel the superheated. Yeah, then it seems that Vf is less than Vg. V is less than Vg, right? So what does it mean? Steam tables are useless in my case. I'm missing so many pages. For next session, I will try to download a better Steam table and then discuss with the students. Yeah, it's very unfortunate from my end. Okay, let me take the help of both of you. Wet state, yeah, exactly. So since you saw that Vf, V and Vg. So V lies within this range. It means that the state of the steam is within the liquid vapor dome, and it's very helpful now because within the liquid vapor dome you have all the values of the steam for all the almost all the states, because we have the steam table. So now you can use the steam table to find the specific volume to find other corresponding thermodynamic properties. So now, since you know the specific volume, let me just help you with this. Since you know V is 0.09 meter cube per kg, and you know Vf and Vg, so you can use this formula, right? Yeah, exactly. You need to find x. That's what I was going to tell you. So you can use this one, find the value of x, and once you know the x, you can easily find the value of h as well, right? H will basically be h is equal to hf plus x hfg, where all these properties of enthalpy are found at P equal to 2 megapascal. So can you please do that? Let us drop entropy as per the suggestion of Professor Anand. Let us drop entropy entirely. Let's discuss enthalpy and internal energy as the thermodynamic properties for today's session. Can you please, and you found out x is equal to 0.903. Wonderful. So can you please tell me what's enthalpy now? You have HF and HFG or HG in the for 2 megapascal in the steam table. Just let me know what you find H as by applying x is equal to 0.903. Two six. Yeah, exactly. It's correct. So let us go to the solution. It's correct. Okay. Just for other viewers, just to verify. So we had at P equal to 2 megapascal, we had Vf as 0.0017 centimeter cube per kg and Vg is equal to 0.9963 meter cube per kg. So the given volume 0.09 lies within this region. So it is in the liquid vapor dome. Okay. So we can find the value of x using this expression, from where we get that x is equal to, yes, thank you so much. So from that we get the value of x is equal to 0.904 or 90.4%, the quality of the steam. Okay. So using the same value of x, you can find, since the steam is in the liquid vapor dome, so we can use the steam tables to find all other properties, right? At the same pressure. So at 2 megapascal, we can find HF as 908.79 and HFG as 1890.7. Okay. So from that, using the value of x, we get that h is equal to 908.79 plus 0.904 into 1890.7 to get h is equal to 2618.79 kilojoule per kg. Okay. Entropy also we can find out similarly, but let us just leave it in this case because we have not defined it. Okay. Okay. This is a very a bit more challenging question. So let us go through it once. Okay. A vessel of 0.04 meter cube, so you get the volume, contains a mixture of saturated water and saturated steam at a temperature of 350 degrees Celsius. Okay. The mass of the liquid is present is 9 kg. So it's not the mixture, okay, but the mass of liquid only. Okay. So mass of liquid is 9 kg. Find the pressure, mass, and the specific volume, the enthalpy. Okay. So you have any doubt? Any doubt? You can please ask. Type it. It's completely fine. Yes, of course, it's important. That's why I am dealing with it, right? But fine, thank you for asking. It's no problem because no. Please don't be sorry. It's good that you asked and it's fine. I just want to say that it's important because if you deal with the problems in your hand, these problems in your hand, then you will be well versed with the concept and take it as something that you need to know for for a subject rather than solving the questions for the exam only, right? You'll understand the subject in a better way and it will help you for the other competitive exams that you're going to give, eventually give, right? That's why. I hope the doubt is clear. Thank you, and you're actually participating so well in the class. So why do you bother? Like, just let us just try to solve it. Okay. Please don't be sorry. It's completely fine. Thank you. Yes. So we need to find the pressure, the mass of the entire fluid mixture, the specific volume, the enthalpy, leave the entropy and the internal energy. So we need to find all these properties at 350 degrees Celsius. We can leave the entropy out just for the sake of today's session and find all other properties. Oh, 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 let me just check, okay, with her. Just 1 second, okay. I think, yeah, just wait 1 second. I think I made a typo, so I will just verify it, okay. Sorry for the mistake from my end, okay. So, oh, yes, exactly. Yeah, that's what I thought. Okay, it's 250 degrees Celsius. Sorry for the typo from my end, okay. If we do it, make it 350, then again, you can solve it for that as well, but unfortunately, I don't have a solution to show you. So let us do it for 250 right now. You can do it 350 as an assignment, but 250 for now. Sorry for a typo from my end. Please forgive me. So can you do it for 250? Find the saturation pressure for 250 degrees Celsius. What do you find it to be? Mm, no. No. Yeah, do it for 250 degrees Celsius. Okay, not 350 degrees Celsius. Okay. Let me check the answers. Okay. Okay. So P is it? Let me just check. Okay, with my table as well. 250 degrees Celsius, right? So my table gives at T equal to 250 degrees Celsius, the pressure is 3.9730. So can you just check it once whether it is 3 point, mine gives at 250 degrees Celsius pressure is 3.9730 megapascal. Is it? Can you just verify it? Yes, exactly. Yeah. Now it is correct. Okay, thank you. So with these values or that row of the table, you can now find other values such as VF, VG, UF, UG, HF, HG, all these. Just note it down and then because that will come out to be handy. Okay. So let us solve it together. It's a difficult problem, so let us solve it together. You can try, of course, you can try and solve it before me as well. But let us try to do it together. The solution. Okay, so we have that VF is 0.0. Okay, 0.001252, Vg 0.05008. Okay, good. So now from this, one thing you can do is you can find the volume of the volume of the liquid, right? How? Vf would be mass of the fluid into the specific volume of the fluid. So mass of the fluid is 9 kg, right? Into 0.001252. So can you tell me what you get? The volume of the fluid now, capital Vf. Okay, 0.001126. Is it? Okay, 0.01. Oh, 01. Sorry. I have written additional zeros. So now you see you have the volume of the fluid in your hand. So what you can do is to find the, yeah, fine, thanks. Just, oh, is it? Can you check decimal places? It seems that, let me just do it myself as well. The decimal places seems to be a bit wrong, but other values are correct. You can just check the zeros that you put while multiplying. It's 0.011268. Okay, just one zero is missing after the decimal point. You can add it. Okay, so now you know that V is equal to, the entire volume is 0.04 meter cube, right? So from here you can easily find the total volume of, yes, thank you, the total volume of the gas, which will be V minus Vf. So it is basically 0.04 minus 0.01126. Can you check? Does it match with your answer? The total volume of the gas is 0.02874. Yeah, exactly. Thank you. Yes. So now from here you can find the specific volume of gas. Sorry, the total mass of the gas. How? Because we know that small Vg is capital Vg by mg, right? So mg would be capital Vg by small vg. Now are you getting why I am finding out small vg? Something is equal to mg by mf plus mg. What is this something? Very crucial property. Not property, I will say, yeah, I can tell it as property. Yeah, Reynolds fraction, yes. Because to find the value of the thermodynamic properties within the liquid vapor dome, you need to know Reynolds fraction. It's a very crucial property, right? So to find out Reynolds fraction, I am trying to find out the mass of the gas. Okay. So tell me what's the value of mg? 0.5748. Okay. Yeah. So now you can easily find out the value of the Dynamis fraction. It would be 0.5748 divided by 9 plus 0.5748. So what does it come out to be? 0.06 exactly. So now I think everything is, yes, mg, yeah, 0.5 yes, it's correct, you can use those values. Yeah. So I think from the now knowing the value of the Dynamis fraction, you can find all other properties, because you know the value of Vf, Vg, Uf, Ug at 350 degrees Celsius, right? It is sorry, 250 degrees Celsius, right? So uh, now since you know Dynamis fraction, you can find the value of all other properties. Okay. So I think okay, just tell me the value of the specific enthalpy. Leave the other properties. It's a simple repetition of the steps. Just tell me the value of enthalpy. We need to save time to solve some other questions as well. That's why I'm just saying. Just tell me the value of the enthalpy. Okay, so let me check the value. It is 118.7 exactly. Thank you. So HF in my table, yes, sorry, in my table is 1085.36 plus 0.06 1716.2. It gives HS, sorry, the net enthalpy is enthalpy, specific enthalpy is 1188.32 kilojoule per kg. Okay. This is just the method of decimal points, but thank you so much. It was exactly correct. Okay, now question number 6. I think I don't need to say it, but just for the sake of knowing, the degrees of freedom for a pure substance at its solid liquid vapor triple point is 0. Thank you. It's correct. Now let me see. Okay, now let us just solve question number 7. I think that would be all for today's session. Rest questions are quite similar. Let's look at question number 7. The specific volume of steam after expansion in turbine is 13 meter cube per kg. Okay. At this pressure, the standard saturated liquid and saturated vapor and specific volumes are 0.002 and 16 meter cube per kg. Okay. The saturation pressure. Oh, I think I'm missing the units. Okay. Just let me. Okay, the specific volume. I'm sorry. So it is 0.002 meter cube per kg. Okay. So find the Dynamis fraction of the steam. Okay. U equal to 1172. No, no, no. Oh, you also you found you as well. Yes, yes. Thank you, Shiva Kumar. Thank you so much. Uh, let us go to question number 7. I said like just to save time, and let us take one more question. So question number 7 is the specific volume of steam after the expansion is 13 meter cube per kg. Okay, so here given V as 13 meter cube, small v. Okay, 13 meter cube per kg. So Vf, I think it's very simple question again. 0.002 meter cube per kg, and Vg is 16 meter cube per kg. So you are asked to find the value of the dryness fraction. 0.812. Yeah, that's correct. Yeah, that's correct. Simply use the formula, this one, that V is equal to Vf plus x Vfg. So x would be V minus Vf, or divided by Vg minus Vf. So it is 13 minus 0.002 over 16 minus 0.002. So we will get it as 0.8123. Okay, thank you. 8123. Okay. So okay, let us take question number 9. 8. I guess I will give the solution in this answer sheet. So for the sake of saving time, let us not do question number 8, but let's go to question number 9. Okay, choose the correct statements in reference to steam tables for water. Okay, the enthalpy of evaporation increases with increase in pressure. The enthalpy of evaporation is highest at the critical point. As the pressure increases, the saturation temperature increases. As the enthalpy of evaporation decreases with increase in pressure. So tell me the correct option or options. C. Okay. Only C. D. Only D, or both are correct? You tell me. I can only take one answer, or and there is only one correct answer. Like either both are correct, only C. Okay. Shiva Srinivas, only the that's interesting. So actually, both are correct. Can you tell me? Okay, let me just do the. Can you correlate now what I said? Yes. Okay. I hope you got it what I meant. So in this diagram, so if, as I mentioned, let us take different color. So if the saturation pressure increases, you'll see that the the latent heat of evaporation decreases, right? Because as we go up, the pressure increases. The latent heat of evaporation is reducing, right? But as you mentioned, the pressure also increases, or the temperature also increases with increase in pressure, or vice versa, right? If the saturation temperature increases, saturation pressure will increase. If saturation pressure increases, saturation temperature will also increase. So both C and D are correct. Okay. And B is wrong because the enthalpy of evaporation is lowest at the critical point. It should not be highest, but it should be the lowest. Okay. And these two are just the opposite, A and D. So C and D are correct. Okay. So thank you. The other two questions, I think you can solve it. It's similar, and the solution I will provide with the solution this presentation. So I hope that's all from my side today, and thank you for attending the session and being so interactive. It's quite helpful for me and the other viewers as well. Okay. Okay, then let's meet on Sunday for this week's week 7's session, and hope that both of you will join as well. Okay. Thank you so much, and let's meet in the next session. Okay. Thank you.